Hello everyone. Thank you for the introduction. I am Akash and I'm presenting the work DX100, a programmable data access accelerator for indirection. This work was done in collaboration with University of Michigan and Los Alamos National Lab. This work was primarily done by Alireza. He's the first author of the paper, he's a PhD candidate, and he works with Professor Reetuparna, which is my advisor as well. You can contact him if you have any questions in the paper. To perform a computation, we need to send data from memory hierarchy to the core. Previous works have shown that data accesses can be expensive. Specifically, it can be 1.5 to 26,000 times more expensive in terms of energy and 1 to 1,000 times more expensive in terms of performance. Therefore, efficient data access matters. We have gathered the results for compute throughput and memory bandwidth for the past 15 years for top 10 supercomputers, and we can very clearly see that there's a growing gap between compute and memory speed. This is also known as memory wall. Modern HPC applications have unstructured sparsity. In this chart, we show the compute utilization of two HPC applications, LinPack and HPCG. LinPack is the dense HPC application and HPCG is the sparse HPC applications. We can very clearly see that for the sparse application, the compute utilization is significantly lesser. This is because conventional microarchitectures are more suited for temporal and spatial locality, but unstructured sparsity cannot utilize the locality. We analyzed the HPC applications and found that there are three common data structures. The first one being sparse data structures, such as compressed sparse row, CSR. The second being graph, which is used in graph representation and analysis. And the third one being unstructured meshes, which is used in unstructured mesh exploration in adaptive mesh refinement-based application. A common factor for all three of them is that they all have indirect memory accesses. Indirect memory accesses such as A of B of I. Conventional cores are inefficient for indirect memory accesses. Let's look at why. Memory level parallelism is limited by the multi-stage buffering, which is the ROB, LSQ, MSHR, and the memory controller request buffers. Secondly, there's a chain of dependencies in the indirect data accesses. This chain of dependencies limits the number of outstanding memory access instructions. Thirdly, this chain of dependencies involve multiple compute and memory access instructions. This results in significant time and energy consumption. We propose DX100 as a solution for the problems. To overcome the limitations of memory multi-stage buffering, DX100 provides direct access to the memory controller by passing intermediate queues and buffers. To address the dependency chain between memory accesses, we hoist loads and stores and perform bulk accesses independently. DX100 also has dedicated address calculation units, and this significantly reduces the instruction overhead. With all the optimizations, we see that we have a very high DRAM request rate, and we also improve on the memory bandwidth utilization. In this design, the core offloads a bulk of data accesses at the tiled granularity. For an example, a group of 16,000 elements at the same time. This approach gives DX100 a future visibility. Let's see how DX100 utilizes the future visibility. Memory systems are organized as a hierarchy of different levels, which is channels, ranks, bank groups, and banks. And these can service DRAM requests in parallel. Conventional microarchitectures inject DRAM requests in an arbitrary order. This results in poor bank level parallelism. As a result, certain level of memory hierarchy may be underutilized. To address this, DX100 interleaves DRAM memory requests across different channels, ranks, and bank groups. This interleaving technique helps enhance the bank level parallelism and therefore improves the memory bandwidth utilization. A DRAM bank is organized as a 2D array of memory cells. When a request is issued, a row decoder activates the target row and copies it into the row buffer. A column decoder then selects the target column within the open row and transfers the data to the external bus. The row buffer here acts as a cache for the activated row. So it is important to maximize the row buffer hit rate for higher bandwidth utilization. In conventional microarchitecture, indirect DRAM requests target random DRAM rows and columns. This results in frequent row buffer misses and limited DRAM bandwidth utilization. But in case of DX100, we reorder these DRAM requests based on the target rows and significantly improve the row buffer hit rate and overall DRAM bandwidth utilization. We analyze the HPC applications to capture the common data patterns and design a general purpose and programmable accelerator. We observe that the three most common types of accesses are load, store, and read, modify, write. Read, modify, write is the one where we load from the memory, modify it, and write it back to the memory. We also observe that significant number of these benchmarks have conditional operations. The prior works do not focus on conditional operations because they do not focus on stores and read, modify, write. Whereas in our work, we focus on stores and read, modify, write as well. So we have to focus on the conditional operations. We also observe range loops where the minimum and the maximum bounds come from the streaming load or the indirect load. These range loops can be small and which can be a problem for bulk data accesses. Based on the study of the HPC application, we propose a general purpose and programmable accelerator with 8 instructions which provide various access types, conditions, address calculation, and range loops. Let's look at an example of how we can use the instruction set to upload bulk accesses to DX100. Here we show an unstructured mesh with zone as the 2D space, the dashed lines are the corner, and the points. This is an application, unstructured mesh exploration, which is an AMR adaptive mesh refinement simulation, such as flag hydrocode. Here I show the UMaze code where we loop over the number of corners, and then these corner volumes are added to the point volumes using corner to point chaser. For DX100, we have bulk accesses. That is why we send 16,000 elements at the same time. Then we have a streaming load of corner volumes. Then we perform a streaming load for corner to point chasers. And finally, a bulk indirect read, modify, write operation. Let's look at an overall architecture. DX100 is connected to the network on chip. It is designed as a modular memory mapped accelerator. It does not require any change in the cores and the instruction set architecture. DX100 is shared by a group of cores, and therefore there is no need for fine-grained atomic operations. DX100 includes 4 functional units: the range fuser, ALU, stream access, and the indirect access. There are other units which help in the communication of DX100 with the core, the caches, and the memory controller. The most important unit is the indirect access, and therefore we'll focus only on that for this talk. Indirect access units receive a tile of conditions, indices, values, and perform a bulk indirect load, store, and read, modify, write. This unit itself has a lot of components. The most important ones here are the row table and the word table. The row table and the word table maintain, reorder, interleave, and coalesce memory accesses. The indirect unit operates in 3 stages. In the first stage, fill, this unit reads a tile of indices from Scratchpad. It generates the corresponding addresses and decodes it into DRAM coordinates. After the decoding, these DRAM coordinates are inserted in the row table one by one. By the end of this stage, The row table maintains all target columns across all target rows. In the request stage, the request generator traverses the row table row by row, and corresponding column accesses for each row are sent into the memory system after reordering, coalescing, interleaving the memory request. Finally, in the response stage, the cache lines are received from memory. The word table is then looked up to locate the target words within the cache line. These words are connected through a hardware linked list architecture. Individual words are extracted from the cache line, and in case of an indirect load, they are stored back to the scratch pad. To evaluate DX100, we have an in-house functional simulator for fast functional verification. Then we use Gem5 and Remulator 2 for core and DRAM modeling. Our evaluation is based on a 4-core system. For the baseline, we have a 10 MB LLC, and for DX100, we have 8 MB LLC and 2 MB scratchpad. This chart shows the performance improvement of DX100 across 12 benchmarks, where we see that the geometric mean of the speed up is 2.6 times. This speed up stems from two reasons. The first one is memory bandwidth utilization, where we can see that there's a 3.9 times improvement in the memory bandwidth utilization. Secondly, there's an instruction reduction. There's across these benchmarks, which is 3.6 times. Because of the hoisting of instructions outside of the loop and dedicated address units. The reason why we have increased memory bandwidth utilization is because of increased row buffer hit rate. We see that we have a 2.7 times increased row buffer hit rate. This is because DX100 has a visibility into the future accesses and can reorder bulk accesses. This increment in bandwidth utilization is also because of DRAM request rate. DX100 is directly controller to the memory controller, hoists the accesses, and significantly increases the DRAM request rate, which is 12.1 times. In summary, indirect data accesses have low memory bandwidth utilization. This is because of the conventional microarchitecture limitations like multi-stage buffering, chain of instruction dependencies, instruction overhead, and irregular accesses. We perform an application study where we see the access types, conditional accesses, the loops, and we propose a general purpose and programmable data access accelerator, which has direct access to the microcontroller, can hoist data accesses, and accelerate bulk accesses. It performs reordering, interleaving, and coalescing of data accesses, and therefore leads to 2.6 times improvement in terms of performance and 3.9 times improvement in terms of bandwidth utilization. We have the GitHub link with the Gem5 changes here, and we'll be more than happy to take any questions if you have any.